Hi, I'm Jon Stapleton with CodeVA, and this is a lecture tutorial thing on PRIMM, which is a computing pedagogical framework. I'm going to talk a little bit about it, provide some definitions and ideas about this concept. Let's jump right in. So, PRIMM is a pedagogical framework for coding educators. PRIMM is an acronym that stands for Predict, Run, Investigate, Modify, and Make. It describes what a novice it describes what a novice coder should do with code as they develop new understandings about how to read, trace, and write programs. PRIMM has been widely studied by the computing education community. You can see some examples there, links in the description. Widely studied about the computing education community. Results indicate that it's a good starting point for many educators to consider as they develop their pedagogical knowledge about coding education. PRIMM isn't the best or only approach to teaching programming. I don't even know how I would begin to determine what would be the best way. It just kind of depends on context. But it's widely used, and it's sort of an important methodological framework for teachers to be aware of. So I'm going to break this down into two kind of sections. First, predict, run, investigate, and then modify and make, because they kind of go together. So first, predict, run, investigate. In this stage of the PRIMM cycle, students are analyzing code examples often provided by a teacher. This analysis takes place in 3 steps. First, students predict. They'll read a program and make a prediction about what it will cause the computer to do. It's not important for students to be exactly correct, but to clearly describe their expectations in order to compare them with results in the next step. Students' predictions in the stage are indicative of mental models or notional machines they have regarding the syntax, the code, and the way the computer interprets the program. Step 2 is to run the program. Then, after students make predictions, they have to actually have the computer execute the program. They're not just going to look at the code and make predictions. They're going to get feedback from the computer. This step is intended to help students identify whether or not their mental models of the program and computer are accurate. Finally, the third part of this analysis stage is investigate. Students will analyze the program and try to trace through what the computer does when it executes the code. During this stage, students should come up with questions they are curious about based on parts of the code they don't understand. These questions can guide direct instruction, provide a starting point for the next part of the PRIMM cycle, or serve as an assessment of students' mental models. The next thing students will do in PRIMM is modify and make. Modify involves making changes to a code example. It can be the code example they did the predict, run, investigate on, or it can be a different code example. There are lots of ways to approach this process. Students might debug and correct broken problems and make changes to working programs to see what impact changing different lines has on the output. They can remove lines of code to simplify an example or extend an example by adding repeated sections or continuing with a pattern that's present in that code example. The modifications students make to the program should be attempts to address the questions they developed in the prior investigate stage. Finally, the last thing students are going to be doing in the PRIMM cycle is writing original code. They're going to write a new program integrating the new coding concept that they did the first couple of stages of PRIMM about. In this stage, students write their own program making use of a new concept they investigated in prior stages. Often, they'll run into errors that require troubleshooting. This is a good idea to have them return to the prior stages of PRIMM when they encounter these problems to analyze the issue and refine their mental models. We're going to come back to this idea of sort of like a PRIMM spiral. The make stage requires synthesis of new information and requires that students transfer new concepts from prior contexts, from the context of pre-written code examples, to whatever problem they've been prompted to work on. And finally, the make stage takes a lot longer than the prior ones. The other ones are like short little examples. Making something from scratch takes longer. It takes a longer amount of time. Now, it's not often appropriate to implement PRIMM in the same way for beginners and advanced programmers. Beginners may not have enough prior knowledge to predict the results of a program in a useful way, and advanced students may not need the scaffolding of pre-written code examples to analyze. I'm going to describe some different ways of implementing PRIMM at different stages of skill acquisition next. So when you're working with beginners, it's a good idea to do like a guided, modified version of PRIMM just throw out the predict stage at first, because students aren't going to have enough prior knowledge to make informed predictions. They might be able to make predictions based on like interpreting the code as if it were a sentence, and that's okay sometimes, but a lot of times if they get it right, they're just lucky, and it's not actually a good cognitive task to practice. You can skip straight to the run, have them make observations, and do some direct instruction to set them up for a future predict stage. Students should be able to make observations about what the program seems to be causing the computer to do, and they should be able to, after seeing some output, make some predictions about what parts of the code they can change to modify that behavior. Then after you kind of do that modified introduction, you can jump into PRIMM, because students will have built up just a little bit of prior knowledge to help make that predict step more meaningful. For intermediate students, you can move through predict, run, investigate pretty expeditiously. They should have some background knowledge. They should be able to apply prior concepts that they've worked on previously to whatever they're working on. And they can find errors. They can predict results more easily. At this stage, it's a good idea to have students start to modify some broken code examples. This will help them with the debugging process and help set them up for success when they start to make their own versions of code of the programs and they're running into sort of like ill-structured problems that are more difficult to work with. With advanced students, they might find the predict, run, investigate stages trivial, especially if you're providing them with sort of like pre-baked code examples where the problems, if there are any, are pretty easy to identify and the concepts aren't as advanced. At this stage, you should work with students to help them transfer their analysis skills to their own projects. You can do predict, run, investigate with student-created code examples, or with code examples from outside of the classroom. You can even have them do predict, run, investigate on their own code examples if they run into troubleshooting issues or debugging problems. It's a good idea to start conceptualizing this advanced stage as a place where students apply PRIMM cognitive patterns to code they have written rather than code the educator has written for them to practice with. PRIMM becomes more of a cycle of like them creating things rather than a cycle of like onboarding new skills. Now, I have a couple of notes about PRIMM that I think are worth highlighting here. I'm just going to go through them pretty quickly. First, students don't need to master predicting and investigating before they start modifying and making. You want to move through PRIMM in like a spiral, where you start with easy concepts and students are making their own code, but maybe the code's not that complex, and then moving through more advanced things, returning to those predict, investigate, modify, make stages. It's really important that students are making their own things early on, even if they're simple. This next one's related. PRIMM's supposed to be a quick cycle around that you move through several times in a given span of instructional time. PRIMM is good over like 1 or 2 class periods, not a semester or school year. And the make step is long, so you want to leave time for that. It's not appropriate to divide the year into a 9 weeks devoted to predict, another 9 weeks devoted to run, etc. Predict, run, investigate, that can happen over like a half hour if you have a well-structured code example. Next, let's talk about assessment. You can use a lot of different kinds of assessment in the PRIMM cycle to help develop insights about students' knowledge and to help support students acquiring new skills. Multiple choice practice questions are great for that predict, investigate stage because it's going to help. Predicting code, that is a multiple choice question, sort of. It's like the exact cognitive pattern that they're going to use to answer multiple choice questions. But they're also going to need higher order programming skills that are involved in the modify and make stage. And finally, super important, PRIMM is not a substitute for direct instruction. You cannot just put code examples in front of students and ask them to read it and predict it. You do need to provide students with explicit instruction on what each command is supposed to do. It doesn't have to take a super long time, but like I said before, and when I was talking about beginner PRIMM, you can't expect students who don't have a whole lot of prior knowledge to be able to predict the output of a program in a useful way. You got to develop that prior knowledge first, and then use PRIMM as a way of deepening skills and knowledge over time. And that is PRIMM in a nutshell. If you have any questions about this, or you have any suggestions or comments, please get in the comments below. We'd love to hear from you. Otherwise, good luck and happy coding.